In section 15.5, we'll be looking at applications of rational expressions. Example 1 asks us to use the formula given to answer each part. So the formula that we're using is 1 over f equals 1 over p plus 1 over q. And that formula comes from example 1 in the textbook, which says that the focal length of a lens is given by this formula, where p represents the distance from the object to the lens, and q gives you the distance from the lens to the image. So that's just so that you know where this formula came from. Alright, so A says find P if f is 15 and q is 25. So the first thing I'm going to do is rewrite it with those values in. So it's going to be, instead of 1 over f, we're going to write 1 over 15 equals 1 over p plus 1 over 25. Alright, so now to solve for p, the first thing I'm going to do is multiply by my least common denominator. So I'm going to look for something that 15 and 25 have in common, which is 75. And then of course I have to multiply by the p also, because it's something that they can all multiply to. So when I multiply 75p times 1 over 15, so the 15 goes into 75 5 times, so, and that cancels the denominator. So that's just going to be 5p. And then on the second case, just the p's cancel and you're left with 75 times 1. And then 25 goes into 75 3 times. So it's going to be 3p times 1 is just 3p. Alright, so now that we don't have fractions and p is part of the equation, then I can just solve it like I've been solving equations. So I'll subtract 3p from both sides, which would give me 2p equals 75. So p equals 75 over 2. In example B, we will be using the same formula. So this time I'm going to plug in p equals 6 and q equals 9, and we're finding f. So this is going to be 1 over f equals 1 over 6 plus 1 over 9. Alright, so my least common denominator, 6 and 9, is going to be 18, so 18f. So when I multiply 18f times 1 over f, the f's cancel, and I'm left with 18 equals, that's 6 goes into 18 3 times, so 3f. And then 9 goes into 18 2 times, so plus 2f. So now I have 18 equals 5f, and then when you divide both sides by 5, we get f equals 18 fifths. And then C, find Q if f is 12, so that's going to give me 1 over 12 equals p is 16, so plus 1 over q. And this time I'm looking for q. So common denominator for 12 and 16 is going to be 48. So that's 48q. 12 goes into 48 4 times, so 4q times 1 is 4q. 16 goes into 48 3 times, so 3q times 1 is 3q. And then on this one the q's cancel, so 48 times 1 is 48. So subtracting 3q from both sides gives me 1q equals 48. Example 2 is going to be similar. We're solving for q. The only difference is I still have 3 variables. So when I solve for q, and solving for q means you want q by itself. Since I still have variables, my answer is not going to be just a number like q equals 5. It's going to be a whole formula. Alright, but I'm going to use the same steps to solve it. So I'm going to multiply everything by the least common denominator, which is going to be PQR. So when I multiply that by the 3 over p, the p's cancel, and this leaves me with 3QR. Then my q's cancel, so that leaves me with 3PR equals, my r's cancel, so 5PQ. Alright, so you need to keep in mind always what you're solving for. I'm solving for q. So I'm going to subtract 3PR from both sides. Okay, so notice I didn't do 5 minus 3 is 2, and the reason is because the 5 is a PQ and the 3 is a PR, and those don't match, so I can't combine them together. Alright, and since I want Q by itself, and the 5PQ has a Q, I'm going to subtract that from this side, move it over. So I want all my Q's together on one side. So I have 3QR minus 5PQ equals negative 3PR. Alright, so again, I'm solving for Q, so I got all my Q's together on the left side, and so I can factor out a Q because they both have that in common. So if I factor out a Q, I'm left with 3R minus 5P. And then since that's Q times 3R minus 5P, I can divide by 3R minus 5P, which cancels, and that leaves me with Q equals negative 3PR over 3R minus 5P. Example 3 is going to be very similar. The only difference is we don't have any constants in this, so we already have it as a formula. It's going to still be a formula, it's just going to be R equals instead of A equals. And then notice our variables are capital R and lowercase r, and those count as different variables. Okay, so I'm going to start it the same way by multiplying by the denominator. So remember, A is A over 1, so I'm going to multiply both sides by R plus R. So when I distribute that, that's going to be A times R plus R equals, and then when I multiply it to this, the R plus R cancels, and it's just capital R times lowercase r. Okay, so remember, I'm trying to solve for capital R, so the next thing I'm going to do is distribute the A, so it's going to be A times R plus A times lowercase r equals RR. Okay, so this step is going to be just like on example 2, where I need all my capital R's on the same side of the equal sign. So I can subtract this AR. So I have AR equals RR minus AR, and then I need to move this capital R over. So I have AR minus RR equals a lowercase r. And then since I got all my capital R's on the same place, I can factor out the capital R, leaving me with A minus lowercase r. And then I can divide because that would get me my R by itself equals AR over A minus R. Oh, and I forgot to bring down that negative. So a negative AR over A minus R. Okay, example 4. In 2006, approximately 11.7% of the 73,740,000 children under 18 years of age in the United States had no health insurance. How many such children were uninsured? Okay, so this is a percent problem, and for percents, you just need to remember part over whole equals percent over 100. Okay, so notice that they said 11.7% is 11.7 out of every 100. So percent means out of 100. So 11.7% of the 73,740,000 children under the 18 years of age had no health insurance. And we're trying to find out how many children were uninsured. So 11.7% is going to be the 11.7 out of 100. This number, you need to decide, is it the part or the total? It's 11% of that population. That's the total, 73,740 million. That's the total population of children under 18. And we're looking for how many of those children were uninsured. So the uninsured is the part. So that's my X. Okay, so easiest way to solve proportions, cross multiply. So 73,740,000 times 11.7. Okay, that gives me 862,758,000. So you multiply diagonally, and then you're going to divide by the number that's diagonal from the X. And then, so when I divide that by 100, shortcut for dividing by 100 is to cross off 2 zeros. So it's going to be 8627580. 8,627,580 is the part of the population that was uninsured. Example 5. Lauren's car uses 15 gallons of gasoline to drive 495 miles. She has 6 gallons of gasoline in the car and wants to know how much more gasoline she will need to drive 600 miles. If we assume that the car continues to use gasoline at the same rate, how many more gallons will she need? And round your answer to the nearest tenth. Okay, problems like these are proportion problems. And the reason I know it's a proportion problem is because I know a ratio at a certain amount. So the ratio that I know is that 15 gallons will get her 495 miles. So I'm going to write 15 gallons will get her 495 miles. So she has 6 gallons in the car. She wants to know how much more gasoline she will need to drive 600 miles. So in order to know that, I need to know how many total gallons it takes her to drive 600 miles. So 600 miles, and it takes X gallons. Now you have to be careful because she already has some gallons to begin with. So you always have to go back to the question and make sure that you answer what they're looking for. Because in this case, I'm just saying how many gallons total she needs to go 600 miles. So here's a proportion. So I'm going to cross multiply. 15 times 600 is 9,000. And then I'm going to divide it by 495. Which is 18.1 18 forever. Alright, so it takes 18.18 gallons to go 600 miles. She already has 6 gallons, so 18.18 minus 6 gallons is 12.18 gallons, and it said round to the nearest tenth. So since the 100th place is an 8, that's going to round to 12.2 gallons. So she needs 12.2 more gallons in order to complete her trip. For example 6, we're going to be using distance, rate, and time formulas. So formulas that you need to know are distance equals rate times time. Once you know that one, you can solve for whatever you want. So if we're looking for the distance, you would use distance equals rate times time. If you're looking for the rate, well, you can find the rate just by solving for r, which means you want r by itself. So if I cancel the t, so rate is equal to distance over time. And then sometimes we'll be asked for time. So in that case, we'll do the same thing, but you divide both sides by r and get t by itself. So time is distance divided by rate. So if you remember distance equals rate times time, you can figure out the others depending on what they're asking you for. Okay, so A says the world record in the men's 100-meter dash was set by Justin Gatlin of the United States in 2006. He ran it in 9.77 seconds. What is his speed in meters per second to the nearest hundredth? So we're looking for what is his speed, which would represent rate. Okay, so rate is the distance over time. So the distance is 100 meters, because it's a 100-meter dash, and he ran it in 9.77 seconds. So 100 divided by 9.77 is going to be 10.235, and they asked to the nearest hundredth. So my hundredth place is the 3, the 5 rounds it up, so it's going to be 10.24 meters per second. Alright, now I tend to not be able to remember these, which is why if you just remember this one, you'll be able to get those. You don't even have to set it up as r equals dt. What I would typically do is, I showed you the way that they were showing you in the book, and how to use the formulas the different ways. What I would personally do is I would just write distance equals rate times time. The distance is 100. We're looking for the rate, and we're given the time 9.77. So then to find the rate, I would divide by 9.77 and get my 10.24 when I divided. So as long as you remember distance equals rate times time, you'll be able to solve these. Example B, the world record for the women's 3,000-meter run was set by Julnara Samitova of Russia in 2005. Her speed was 5.539 meters per second. To the nearest second, what was her time? Okay, so this time we're looking for time. So let's go ahead and just set it up as D equals rate times time. So the distance is 3,000. The rate is the speed, is 5.539. And we're looking for t. So to find t, we'll just divide by 5.539. and that comes out to 541.6, and it says to the nearest second, so about 542 seconds is the time. Now if you remembered the formula the other way, or if you went ahead and figured it out at the beginning, so T equals D over R, you could just plug it in directly that way. So the distance was 3,000, the rate was 5.539. You would still get the same thing. You're still doing the same amount of work. It just depends if you want to solve for it when it's still in formula form, or if you want to solve for it after you put the constants in. C. A small plane flew from Chicago to St. Louis, averaging 145 miles per hour. The trip took 2 hours. What is the distance between Chicago and St. Louis? So distance equals rate times time. Averaging 145 miles per hour, so miles per hour is my rate. 2 hours is my time. What is the distance? So we're looking for D. So 145 times 2 is 290 miles. The previous examples tended to be very straightforward. As long as you read it and you understand what they're asking you for, and you recognize if it's a proportion problem or if it's a distance equals rate times time problem. Examples 7, 8, and 9 tend to be a little bit more involved. There's more details in it. And so I'm going to very strongly recommend that for these types of problems, you make a table and fill out information in the table, and then get your equation from that information. So example 7 says a plane travels 100 miles against the wind in the same time that it takes to travel 120 miles with the wind. The wind speed is 20 miles per hour. Complete the table. So the table has the two things that we're comparing. So we're comparing when it goes against the wind and when the plane is traveling with the wind. And then we're going to fill in the information that they give us. So it travels 100 miles against the wind. So that's the distance that it's traveling against the wind. So distance is 100 miles. In the same time, so we need to note that the times are equal. That it takes to travel 120 miles with the wind. So again, that's distance. The wind speed is 20 miles per hour. So for my rate is the rate of the plane plus or minus the wind. So we are trying to find out what the speed of the plane is. And we need to keep in mind that when it's going against the wind is slowing down the plane. So that's why my rate is x minus 20. When it's going with the wind, you have the plane going at a certain rate, plus the wind is pushing it faster. So that's where we get our x plus 20. So against the wind, you subtract the wind because it's slowing it down. With the wind, you add the wind because it's pushing it faster. So now remember that our formula is distance equals rate times time. So in this case, I'm trying to fill in values for t. So if I solve for t, that means I want t by itself, so I'm canceling the r. So time equals distance divided by rate. So I'm going to write in my time as a ratio of distance over rate. So this is going to be 100 over x minus 20, and this is going to be 120 over x plus 20. And then remember that it said it was in the same time. We made a note that these were equal. So for part B, find the speed of the plane. My equation is going to be 100 over x minus 20 equals 120 over x plus 20. So then I can solve that. My common denominator is going to be x plus 20 times x minus 20. So my x minus 20 cancels out, and I have 100 times x plus 20 equals, and the second one, my x plus 20 cancels, and I have 120 times x minus 20. So I'll distribute those. And then get x by itself, so subtract 100x. It's going to give me 20x, and then I can add the 24 from that side. So then dividing by 20 gives me x equals 220. So the plane itself is traveling 220 miles per hour. Example 8 says Kathy Manley drove 300 miles north from San Antonio, mostly on the freeway. She usually averaged 55 miles per hour, but an accident slowed her speed through Dallas to 15 miles per hour. If her trip took 6 hours, how many miles did she drive at the reduced speed? Okay, so when they're asking us how many miles did she drive at the reduced speed, this is what my x is. So I'm usually going to put x to whatever we're looking for. So the reduced speed is x, the distance at the reduced speed is x. And so we know that my total trip was 300 miles. So if she drove x amount at the reduced speed, the miles in the total speed would be, the miles in the normal speed would be the total 300 minus whatever she did here. Okay, so that's where those came from. Alright, so then her normal speed was 55, so that's the rate, and the reduced speed was 15. Okay, and then about time, it says her trip took 6 hours. So the time is going to total to 6 hours. So again, if I know distance equals rate times time, then time equals distance divided by rate. So I'm going to write the time as 300 minus x divided by 55 and x over 15. And this time they're not equal to each other. This time they total to 6 hours. So it's going to be 300 minus x over 55 plus x over 15, and that total is 6 hours. Alright, so now I can solve. So a common denominator for 55 and 15 is going to be 165. So 55 goes into 165 3 times. So 3 times 300 minus x plus, and then 15 goes into 165 11 times, so 11 times x, and then 165 times 6. Okay, so this is going to be 990. And that's going to be 900 minus 3x. So negative 3x plus 11 is 8x plus 900 equals 990. Then when we subtract the 900, I get ax equals 90. So x equals 90 over 8, which is 45 over 4. So I could probably leave it as 45 over 4, but since we're talking about how many miles I mean, if I told you I drove 45/4 miles, that probably wouldn't make a whole lot of sense to you. So since we're talking application problems, you want it to make sense in real world terms, I would go ahead and change that to improper. So 4 goes into 45 11 times with one remainder, so 11 1/4 miles. Alright, so the last two examples were still dealing with distance, rate, and time. They were just a little bit more detailed, and so we used a table for that. Example 9 is an example of a work rates problem. Okay, so we're going to make a table for this, but notice that the labels on the table are going to be different. It's not distance equals rate times time. We're not talking about distance anymore. Alright, so our problem is Stan needs 45 minutes to do the dishes while Deb can do them in 30 minutes. How long will it take them if they work together? So you're going to use this type of table with rate, time working together, and fractional part of the job done. Every time you have any kind of problem that two people are working on a job, how long will it take one person to do it by themselves, or how long will it take both of them to do it together? Another example of work rate problems are like if you have an inlet pipe and then a drain pipe. So you have water running in at a certain rate and it can fill a pool after so many hours. But if you have the drain open at the same time, how long will it take for the pool or the tub to completely empty with both of them open? So anything like that where you have two things working together for one job to happen, that's going to be a work rates problem. Alright, so our table, the rate is always 1 out of however long it takes to do something. So if it just said time, we would put 45 minutes, but the rate is going to be 1 out of 45, 1 out of 30. Okay, so the 45 and the 30 come from here. Since it's a rate, it's going to be 1 out of 45, 1 out of 30. The numerator is always going to be 1. Okay, then time working together, that's what they're asking for. They're asking how long will it take them if they work together. So since that's what they're asking for, that's what's going to be X. And then the fractional part of the job done. Well, if they work at a rate of 1 out of 45 for X number of minutes, he's going to have X out of 45 part of the job done. Then same thing for Deb. She'll have X out of 30 part of the job done. And then this always totals to one job complete. Always. Okay, it's not like the other one where, you have to read it real carefully to see how the times are related. On this one, you're always going to end up with one job complete. So I'm going to take X over 45 plus X over 30 equals one complete job. So then to solve for it, they both multiply to 90. That's my least common denominator. So 45 goes into 92 times, so it's going to be 2x. And 30 goes into 93 times, so plus 3x. And then don't forget to multiply the 90 times 1. A lot of people forget that. So 5x equals 90, and x equals 18. So that means it's going to take them 18 minutes to do the job together. B says, suppose it takes Stan 35 minutes to do the dishes, and together they can do them in 15. How long will it take Deb to do them alone? So this time I'm not trying to find out how long it can take them together, but we want to know how long it would take Deb to do it by herself. So remember, my labels are rate, time working together, and fractional part of the job done. Okay, so it takes Stan 35 minutes by himself. So the rate, if it takes him that much time, the rate is going to be 1 out of 35. And we want to know how long it will take Deb to do it by herself. Well, we don't know. So her rate is 1 over x. It takes them 15 minutes to do the job together. So that's going to be 15. And then, so the fractional part of the job done, it's the rate times the amount of time they spend. So Stan works at 1 out of 35 for 15 minutes is going to be 1 over 35 times 15 over 1 is 15 over 35. And I can simplify that. They're divisible by 5, so 3/7. So Stan has 3/7 of the job done. Now Deb is working at a rate of 1 over x also for 15 minutes because it takes him 15 minutes to finish the job. So then the fractional part of her job done is going to be 1 over x times 15 is 15 over x. And remember, they always total to one job. So it's going to be 3/7 plus 15 over x equals 1 whole job. And then common denominator is going to be 7x. So the 7's cancel, so that's 3x plus, now the x's cancel, 7 times 15 is 105. And then don't forget 7x times 1. So subtracting 3x gives me 4x. So 105 over 4. And then remember, you want to put this in terms that make sense. I wouldn't say, oh, it takes me 145 over 4 minutes to do something. Okay, so I'm going to go ahead and divide that out. So 4 goes into 105 26 times, and a fourth. So it's going to take her 26¼ minutes, which is 26 minutes and like 15 seconds to do it by herself.